that introduction. Very, very nice to be here. Wish I could be there in person, but very glad to have a chance to talk with you all. What I'm going to talk about today is an issue that came up as we revised the textbook that we wrote on quantitative bias analysis. I recognize that this is probably a fairly mixed audience and not everyone knows that much about quantitative bias analysis. So I will give some insight into what that is and how it works. So I do apologize to those of you who've heard me talk before. You're going to have to see some of the same things that you've seen before. But the question that came up is, when you think about trying to account for sources of bias in your analyses, we're very comfortable thinking about how to account for random error. We have p-values and confidence intervals and all those sorts of things. We don't often really account for systematic error in a quantitative manner, but we can, and that's what quantitative bias analysis is all about. But it turns out it's not as clear as I always assumed it was what is actually systematic and what is random error when it comes to bias analysis. So that's what I want to talk a little bit about today. I'm going to focus on measurement or misclassification issues in this talk, though we could talk about confounding or selection bias. But measurement error, misclassification in particular, is something that is near and dear to my heart. If you've heard me talk about this before, you know that I think that measurement error is probably the biggest problem that we face in epidemiology. And this example to me sort of exemplifies it. So this is a figure that shows the relationship between human papillomavirus infection and invasive cervical cancer. And the estimates are in chronological order. So that if you look in 1987, the estimates were anywhere, sort of roughly in the neighborhood of an odds ratio of 7 or 8. Whereas when you got to 2003, as the tests for HPV got better and better and better, the odds ratios end up in the neighborhood of like 800. So an order of magnitude that we're missing. And this is because of measurement error, and it speaks to this issue that if we can't measure things well, sure, we can detect that there is a relationship, but how big is that relationship is what matters in terms of public health action. An odds ratio of 8 is a problem, and we should do something about it. An odds ratio of 800 is a public health emergency, and we should drop everything and immediately move to action. So this has real cost in terms of lives saved. So when we think about misclassification problems, we need to think about how we describe misclassification. So the two ways that we typically think about it is either in terms of sensitivity and specificity or in terms of positive and negative predictive values. Sensitivity and specificity, that's when we have truth in the denominator. Positive and negative predictive values are when we have the test result in the denominator. And we can use either one of these to characterize the amount of misclassification for any particular variable that we're interested in. And there's a nice relationship between positive and negative predictive value and sensitivity and specificity. And those relate to each other as a function of, well, I should say the predictive values relate to the sensitivity and specificity in terms of those values themselves, but also in terms of the true underlying prevalence of the variable that we're interested in. If it's an exposure, then that's the true underlying prevalence of the exposure. And knowing the relationship between those two parameters, those two sets of parameters, is going to be really useful if we want to think about how we could account for misclassification in our estimates. Because there's actually a fairly simple relationship between the data that we observe in our study, which I have on the left, and what I'll call the expected true data, the data that we would have observed had we not had misclassification. And in this case, I'm referring to an exposure being misclassified. And this set of formulas on the right shows how we could go from the observed data to what we would expect the true data to be if we knew what the sensitivity and specificity were. And it's not particularly complicated, that formula. And so what that means is if we have reasonably good validation data on the misclassified variable, then we can adjust our observed estimate very simply, much in the same way we could adjust for measured confounding using simple regression models. So this is really simple and easy to do, and certainly the formulas to do this have been known since the 1950s and 60s. So the fact that we don't do it seems to me fairly problematic because it's very simple and easy to do. And this is again an example of what we refer to as quantitative bias analysis, assessing the amount of bias that we would expect to be in our observed data if we know what the bias parameters are. In this case, the bias parameters are sensitivity and specificity. And so let me use a quick example, one that if you've heard me talk before, I love because it's such an easy one to understand. It relates to a study that a colleague of mine did in which he was interested in the relationship between smoking during pregnancy and incident breast cancer. And she did her study as a case control study in a registry in Massachusetts. And she found no relationship between smoking during pregnancy and incident breast cancer risk, which was at the time was in contradiction to the only other studies that had been done, which showed a strongly increased risk. Now, the reason why it's such in my opinion, a great example is because Eliza got her data on smoking during pregnancy from a question that's asked on the Massachusetts birth certificate. So they ask the question of the mother after she's given birth whether or not she smoked during pregnancy, and everyone can sort of easily identify that that is a problematic way to get that information, particularly in terms of sensitivity, right? We don't think that many women are going to say they were smokers when they weren't, but you can imagine a lot of women who did smoke during pregnancy would say that they didn't, because social desirability, people know they're not supposed to be smoking during pregnancy. And so you could see a large underestimation. And there's been a lot of validation studies done on these data collection methods. And you can see that in these various different studies, and these were done in various different ways, the specificity is always near one, right? Very few women say that they smoked during pregnancy when they didn't, but sensitivity can be quite low. In fact, in some cases, it's as low as 30%. For the moment, let's pretend that this was the true underlying sensitivity and specificity. So it's 78% sensitivity and 99% specificity. Let's say we did an internal validation study in our own data. Well, we have put together some spreadsheets that will allow you to very quickly adjust for the misclassification using those values. And this is what we refer to as simple bias analysis. So you can see here we have spreadsheets. In the blue is where you input your data. In the green is where you get the adjusted results. And so I've input the data in blue, and I've also input the values for sensitivity and specificity in the cells in the top right. It's a little hard to see, but I've input the values from that particular study. We're going to assume non-differential misclassification. Therefore, the expectation is biased towards the null. So our adjusted estimate should be away from the null. And that is exactly what you see. So I've blown up the observed estimate, which was an odds ratio of 0.95. And then if you look at the adjusted estimate, after we account for the poor sensitivity, the point estimate actually doesn't move at all. Because even though it seems pretty obvious that there's a lot of misclassification going on here, the fact that there is a lot of misclassification, poor sensitivity, actually makes almost no impact on this particular result. This result is just not, pardon the expression, sensitive to the estimate of sensitivity. And that's a really useful piece of information, because even though our intuition says this is going to be a really poor data collection method, it actually turns out it's perfectly fine. And we shouldn't put a lot of energy into getting better estimates of smoking, because the money that we're going to have to put into that isn't going to get us any better estimate. And so it's a really powerful way of demonstrating the impact of bias by simply quantifying the change in estimate. In this case, it's almost null. Now, this assumes, of course, that we know with certainty what the bias parameters are, and we never really know what they are. So we wouldn't really want to stop here with these simple methods. But before we go on to talking about how we could use sort of more probabilistic approaches, I just want to stop for a second and think about the fact that, remember, we said that the expectation here was biased towards the null. And in fact, there was bias towards the null. The adjusted estimate is actually away from the null, but it's so small that you can't even see it. When we round, the estimate actually doesn't change at all. But it's important to remember that this is an expectation. When people say, non-differential misclassification biases towards the null, they're talking about the expectation. On average, the bias is towards the null when we have non-differential misclassification of a dichotomous exposure and a dichotomous outcome. But imagine a scenario like this one where I knew the true data for a case control study in which the odds ratio was 2, but it's not a particularly large study. And so I can do the same thing that I did in the previous slide and do a simple bias analysis if I know what the sensitivity and specificity are. Let's say, in this case, the sensitivity and specificity are both 90% non-differential misclassification of the exposure. So I can do that same simple bias analysis method, and you can see on the right, my expected adjusted estimate is 2.1. Again, the bias was towards the null, so my adjusted estimate is away from the null. Now, that is what happens in the expectation. But remember that misclassification actually happens to individuals. It's a coin flip, right? So for each individual, I have a probability of being correctly classified that's equivalent to a coin flip of 90% with 90% probability. Well, I can do that for each of the individuals in the data set, flip the coin, and then calculate the adjusted estimate. And I can do that over and over and over to see what the distribution of adjusted estimate looks like. And it looks something like this. So 2.7, that's the true value. All of these results, so this is a histogram of all of those 10,000 results. And what you're looking at here is what looks like sort of almost a normal distribution. And all of the results to the left of the truth represent cases where the bias was towards the null, which is what we expected, bias towards the null. And this distribution is centered on 2.1 because that is where the expectation is. But you can see in a minority of cases, the bias was actually away from the null. Not often, but sometimes that happens. And so we have to keep in mind that this is a probabilistic process happening to individuals. And so that sort of begs an interesting question, which is, does that probabilistic nature count as systematic error or random error? To my mind, when I always thought about this, to me that would be systematic error, because even though I'm dealing with a probabilistic process, it deals with the systematic error, which is the misclassification. So I would lump that under systematic error. But it does beg the question of what is systematic and what is random error. And so we'll think about that as we move into thinking about probabilistic bias analysis. So as I said to you, we don't really know what the bias parameters are in any analysis. We have an idea of what they are, say if we've done a validation study or we've gone to the literature. And so I could have, for the example that I used with Elise's data, I could have chosen different values for the sensitivity and specificity based on those different studies, those different validation studies. And you can see these are the results that I would get using those different values. But instead of doing a bunch of simple bias analyses, I can also quantify my uncertainty in those bias parameters by putting distributions around the values of sensitivity and specificity. And then I can use Monte Carlo methods to simulate, to draw from those distributions, adjust the data, and then do it over and over again to get a distribution of adjusted estimates. And now I'll get a measure of central tendency like I get with a normal, a standard analysis, like a point estimate, and I can get a distribution of adjusted estimates. But if I get a distribution of adjusted estimates, again, I can ask the question of what in that distribution is systematic error and what is random error. Now, to do this, I need a couple of distributions that I'm going to use. One is the binomial distribution, which has two parameters, number of trials and p, the probability. So, essentially a coin flip with some probability that I flip a number of times. So here you're looking at, on the bottom, a coin flipped 100 times with a probability of 0.5. The center of the distribution I would expect would be for it to come up heads 50 times, but it's not unusual to get 60 or even 40. Second distribution is the beta distribution, which is a distribution that has a range between 0 and 1, has two parameters, alpha and beta, and it has a mean at alpha over alpha plus beta. That's a useful distribution for summarizing things like probabilities, say, like sensitivity and specificity. So we'll come back to that. So I can use the beta distribution to summarize my uncertainty in the bias parameters. So say I did a validation study where I had both the birth certificate measure of smoking on the left, and then I went to a medical record and got information on smoking. So I can now calculate the sensitivity and specificity, but those are measured with random error, right? There's sampling variability in there. And so I could summarize that with a beta distribution by using the number. So here for sensitivity, I can use the number of correctly classified people as my alpha parameter. I can use the number of incorrectly classified people as my beta parameter, and I'll get a distribution that ranges between 0 and 1, but is centered on the midpoint of on the value that I got in the validation study of 0.78. Or I could do the same thing with specificity. I could take the number of people who were correctly classified as non-smokers as my alpha parameter, the number incorrectly classified as my beta parameter, and now I get a distribution that is going to be centered on 0.99. And how wide this distribution is going to depend on how much data I have in my validation study. So now I can use that to summarize my uncertainty, and I can run my Monte Carlo analysis. But here's where we start to get into a bit of tension that we came upon when we wrote the first version of this, the code to do this. So when we wrote our textbook trying to describe how we did this, we talked about different approaches for summary methods and record level corrections. Summary methods meaning I just want to adjust my 2x2 table. Record level corrections means I want to run simulations in my actual data set. The summary methods are really nice because I don't need anyone else's, I can do this on somebody else's data as long as they've published their 2x2 tables. And then all I have to do is specify a distribution for my uncertainty in the sensitivity and specificities. If I have record level data though, then I can apply the corrections to individuals. I do have to turn sensitivity and specificity into positive and negative predictive values to do that, but that's not super hard to do, as we'll see. And I can then run that over and over and over, whether I'm doing summary level or record level, and I can summarize the results in a distribution. The main difference between the two, at least as we originally conceptualized it, is summary approaches are only working on the expectation. Record level allows that variation that we saw earlier, in which even when the expectation is towards the null, I can get some values in which the bias is away from the null. So record level seems to have an advantage in that it better approximates the entire uncertainty, but I can only do it when I have my own data. It's also computationally really intensive. And so let me show you the difference. So in terms of the steps we laid out for summary level bias analysis, we would start with a summarized 2x2 table. We would specify probability distributions for sensitivity and specificity, and then we'd randomly sample from those distributions use the same simple bias analysis methods we just looked at to adjust for, in this case, exposure misclassification. And then we would summarize the adjusted contingency table somehow, a relative risk, or risk difference, an odds ratio, whatever you're interested in. And then we'd save the adjusted estimate. We do it over and over again, say 50,000 times. Then we'd also want to think about the random sampling error that we had in our original estimate, so we can add that back in as well. And then I can summarize this using the median as a point estimate, and it can create an interval from the 2.5th to the 97.5th percentiles of that distribution. That's summary level. If I want to do record level, everything is exactly the same, except I add in a few more steps. So the only thing that's changed is, number one, I start with record level data instead of summary level data. And then these 3 red steps, the first thing I have to do is I have to take the sensitivity, specificity, and the prevalence of the exposure that I got from step 4 when I did my simple bias analysis correction, and turn those into positive and negative predictive values using the formula that I showed you when we talked about the relationship between them. And then, instead of adjusting the summary level data, I can apply the positive and negative predictive values to individuals using Bernoulli trials, essentially a binomial distribution with just one trial. And then I can adjust the exposure for individuals. But then I do everything else like I did before. I summarize the data into a relative risk or an odds ratio or risk difference or hazard ratio, whatever it is, with the one advantage being that I can also now use a regression model if I want to adjust for other confounders, but I do everything else exactly the same. And so we have these spreadsheets that we programmed that can run these analyses. Now, ultimately, you probably don't want to use spreadsheets to do this. It's not, spreadsheets aren't designed for it. You want to move to your SAS or your Stata or your R. But spreadsheets are really nice because you can actually visualize what's going on, and it's helpful for just learning the approach. And so we had spreadsheets for summary level corrections, and then we had SAS code that we used for record level corrections. So you can see here, just like before, you input the distributions for the sensitivity and specificity in the blue, you enter the data in blue, you tell it how many simulations you want to run, and you hit the run button. And all the stuff over here is doing all the calculations and all the simulations, and you get your results down in the green. So here's what you get if you put in a sensitivity and specificity distributions using beta distributions. I got these from the example that I used on the previous slide when I showed you the beta distributions, but they have, again, a mean sensitivity of 78% and a mean specificity of 99%, using the same example, smoking during pregnancy and incident breast cancer. Remember, the observed result was an odds ratio of 0.95, so basically a null estimate. And then on the left, I have the results from a summary level bias analysis correction. And on the right, I have the results from a record level bias analysis correction. You can ignore the sort of the middle line, but if you look at the total error, so you can see the point estimate is 0.95 in both cases. But if you look at the intervals that describe both the systematic error and the random error, and I'll come back to what's in there specifically later, you can see that the record level approach on the right gets you slightly wider intervals. Why? Because I'm not just working with the expectation, I'm working with the actual record level data, which means, again, I can get, even though the expectation is biased towards the null, I can get in some iterations bias away from the null. And so the expectation is the same, so the point estimates don't shift, but now I'm doing a better job of incorporating all of the uncertainty that comes about when you apply classification methods to individuals. You can see there the intervals are not that different in this case because there's not a lot of variability when you apply to these individuals. We'll talk about why that is in a minute, but the results are similar, but they are not the same. Okay, so that's how we set things up in the first version of the textbook. Now, we started revising the textbook a couple of years ago, and as we did, we brought on a new third author, Rich McElhose from the University of Minnesota, Tim Lash being the other co-author of the textbook. And we started to think about this difference between systematic and, between summary level and record level approaches. Now, the reason why we had different approaches for summary and record level originally was because it's really hard to do record level corrections in a spreadsheet. You have to simulate a data set and then run the simulations on the data set. And it gets so, the spreadsheets run very slowly to begin with, but they get even slower if you try to simulate a data set, especially if your data set is really large. So obviously that's not a good excuse, but it is the reason why originally we had different approaches. But Tim Lash was the first to point out that you don't actually have to create a full data set to do record level corrections on the summary level data. All you need to do is apply probabilistic adjustments to the cells, I say using the binomial distribution, rather than just fitting the expectation, right? Choose a random number of people in the adjusted cell count that is centered on the expectation, but allows for that variation, and you'll be doing the exact same thing as you're doing in the record level correction. And so we changed the method by which we do this in the newer versions of our spreadsheet. So now everything in the what do you call it, algorithm, I would say, is the same as the record level correction from before, except that you notice we start with the summary level data set, but then everything else follows the same way that the record level correction would, except for two things. Number one is we realized you actually have to sample the prevalence. You could get the prevalence from the expected adjusted data, but you're probably missing some variability in there. So we actually sample the prevalence as well. But then if you look at step 4D, we then apply the positive and negative predictive values to the cells using binomial distributions rather than applying positive and negative predictive values to individuals using Bernoulli trials like we do in the record level correction. But everything else is exactly the same. And that's why when you now run this, we get the exact same results in the summary level that we got in the record level correction. I don't have both here, but the width of this interval is exactly the same as what I previously got in the summary level approach. So you can actually do the equivalent record level type approach using summary level data. The disadvantage is I can't do a more complicated analysis where I adjust for all different kinds of confounders. So let me just walk you through just a little bit of what's happening so we can start to think to answer the main question here that I want to answer, which is what's systematic and what's random error. So I'm just going to show you key parts of the spreadsheet so you can see what's actually going on. So the first thing we do in this approach is you enter the summarized data, which I have down here. Notice the labels are wrong. These should say smoking and breast cancer. I forgot to change the labels, so my apologies for that. But on the top, there appear to be timers in my slides. I don't know where they came from, so I apologize for that. And then I enter the beta distributions that summarize the amount of the distribution for the sensitivity and specificity. And then I tell it I want to run 10,000 simulations. Then what the spreadsheet does is from that distribution that I've specified here for the sensitivity and specificity, it's going to sample values from those distributions. So the first time we run it, it chooses sensitivities of 0.98 and specificities of 0.909. It then uses those sampled values to adjust the observed data, assuming that those are the correct values. So it takes the observed data. This is a different data set, so you can ignore the labels. That's why the labels were wrong in the previous one. It takes the observed data, applies these values of sensitivity and specificity, and gets these adjusted values. And in the spreadsheet, they look like this. Now, from those values, I could now calculate the expected true prevalence of the exposure. For the cases, that's just going to be 36.42 divided by this total. And for the controls, it's going to be 166.48 divided by the total. But I want to account for the fact that that's an estimate, so I have variability there. So what I can do is I can sample from a beta distribution centered on the same value that I get for the expectation for the prevalence, which is 0.294. And I do the same thing for the controls. Sample centered on a value of 0.132, which is the actual expected prevalence that I got when I adjusted. But it allows for that variability because it's an estimate. So that's what it looks like in the spreadsheet. Now that I've sampled the prevalence, and I know what the sensitivity and specificity are, at least I've sampled them, I can use those formulas that we had in the earlier steps to adjust the data. Sorry, not to adjust the data, to estimate the positive and negative predictive values. So that's what I've done here on the right. These are the 4 values for positive and negative predictive values that I got from the values for sensitivity and specificity that I chose, plus the sampled value for the prevalence. Now that I have the positive and negative predictive values, I can use those to adjust the cell counts. And so that's what's happening here. Here's my observed data on the left. Here's one sampled version of that data, in which the way I've done the sampling is I've said, take these 45 people here. They were classified as exposed cases, and run a binomial distribution, sample from a binomial distribution with a probability of correct classification of 0.81798. That value is the positive predictive value amongst the cases that I calculated in the previous step. And I also say, take these 94 classified as unexposed cases and sample from a binomial distribution 94 times with a probability equal to 1 minus 0.6232. 0.16232 is the positive predictive value amongst the unexposed. And I can do that, I can do that for, sorry, I did that wrong actually. That number 0.6232 is wrong. It should be the negative predictive value, excuse me. So I have the wrong number written there because they are classified as unexposed. But then I can do the same thing for the controls, and that's going to give me a number of people in each of my 4 cells. It's not going to be exactly what the expectation was, but it's going to be close because I'm sampling from distributions. And so this allows me to account for the variability that I would get if I was applying these adjustments to individuals. And then I just do this over and over, and I summarize it each time with a relative risk or an odds ratio. In this case, we want to use the odds ratio because it was data from a case control study. And I do this over and over, and each one of these lines represents just a version of the simulations that I can then summarize where this distribution lies. And that's what we did. So we ran that simulation 10,000 times. And then I looked to see where is the median value of all those simulations. The median value is 0.95. Again, suggesting that the bias was towards the null, the adjusted estimate is away from the null, but in this case, indistinguishable, because when we round, the observed estimate was 0.952 as well. So in this case, you're observing almost no change in the point estimate. But what you're looking at here on the bottom, this is the realized sampled sensitivities and specificities. So you can see that the sensitivities are centered at about 0.78, but it's a distribution that trails off, so it's right skewed. And then the specificities are very tightly bunched around 0.98, which is where we centered the distribution. Again, right skewed, but much narrower distribution here. So we now use that and we come up with an interval that accounts for all of the uncertainty in our results. 0.66 is the 2.5th percentile of that distribution. 1.36 is the 97.5th percentile of that distribution. So if you compare that to the conventional 95% confidence interval, this interval is wider. Wider because it has to account for the fact that I don't know what the bias parameters are, and therefore I have to have less confidence in my results after I run the bias analysis than I did before. So just to make the point, what is included in each of these intervals? Well, the conventional interval only includes the conventional random error. This systematic error interval, which I won't really focus on, is supposed to only include the systematic error. So only the error that comes about from the systematic error, which is, in this case, the misclassification. And then the total error interval is supposed to account for all the sources of error, the systematic error and the random error. And so that's why the total error interval should always be wider than each of the two remaining intervals. Because again, I want to account for all the sources of uncertainty in my data, both systematic error and random error. And so that's where we get back to the question that I really wanted to answer here. So I said to you in the beginning, as I conceptualize this, systematic error is anything that refers to the systematic error process, which is to say, systematic error is anything that relates to, in our case, the misclassification. So there are these various sources of error or variation in the data set that comes about. So one is my uncertainty in the bias parameters. I didn't know what the sensitivity and specificity are, so I had to express that uncertainty using my beta distributions. Then there's variability that comes about from sampling the prevalence of the exposure in order to turn the sensitivity and specificity into the positive and negative predictive values. Then there's random variability that comes about from applying the positive and negative predictive values to the records or the cell counts. And then there's random, sampling error, the conventional random error. The way I always saw it, or at least the way I originally classified this, I would say that those first three all relate to the misclassification, and therefore that is systematic error, uncertainty. And the bottom is the sampling error, the conventional random error. So that's your random error. And so if we separate those two out, the first three go under systematic error. The fourth goes under random error. But as Tim Lash and Rich Mackel has pointed out, well, if you really want to know what's systematic error and what's random error, all you have to do is increase your sample size, because systematic error is error which does not go away as sample size increases. Random error does go away as your sample size approaches infinity. So if you increase your sample size, you can just look at which one of these goes away, and those fall under random error. It's equivalent to this example that we looked at in the beginning, where I ran the simulation 10,000 times on a fairly modest sized data set, and we saw that most of the adjusted estimates, the adjusted estimates were towards the null, but a small proportion of them are away from the null. But if you think about this example, if the data set gets larger and larger and larger, it will converge to the expectation, right? All the results will end up at the 2.1, which was the expected estimate. And so if my data set was really large, this idea that non-differential misclassification biases towards the null, but it can bias away from the null, goes away, because I'll hit the expectation rather than having this sort of variability in my different results. And so then if you look at it this way, it actually becomes clear that my original thinking on this was wrong. Because if you increase the sample size, the prevalence of the exposure in the misclassification setting approaches the expectation, right? I can flip a coin with a probability to sample what that prevalence is, but if my sample size is incredibly large, I'm going to converge to the expected prevalence. And it'll be exactly the same as doing that simple bias analysis. The same is true of flipping the coin to decide who is misclassified and who's correctly classified. I will converge to the positive or the negative predictive value as my sample size approaches infinity. And then, of course, the random sampling error goes away as my sample size approaches infinity. The only thing that remains as sample size approaches infinity is my uncertainty in the bias parameters. And therefore, that is the only place that there is variability in the estimate of systematic error. Now, we can argue about whether or not it's truly has variability, and I'll come back to that as the last point I want to raise. But it turns out that there are aspects of systematic error which follow random error processes. If I know that I have a misclassification mechanism, and that mechanism applies to individuals in a probabilistic manner, the systematic error component of that is the expectation. The random error component of that is the variability that comes about from applying probabilities to individuals, and that random variability goes away in a very large sample. So it converges to the expectation. And in fact, if I have an incredibly large data set, my estimates, when I only account for the first three sources of variability, converge to just doing a simple bias analysis. It converges to the expectation, which is to say it converges to the original way that we argued for doing these analyses in the first version of the textbook. So I wasn't completely wrong. I was just living in a world in which everyone had infinite sample size. So it turns out that, you know, what is systematic error and what is random error isn't always completely obvious, but you can figure it out by just working through the problem in terms of sample size approaching infinity. But it raises two other sort of interesting questions here, which is, the first one is, if probabilistic application of misclassification is part of random error, why does it not get accounted for in my conventional random error? When you calculate a conventional p-value or confidence interval, you're not accounting for the randomness in the misclassification mechanism. That's because it stems from a systematic process. It's just a systematic process that then applies to individuals probabilistically. Again, not that this is a big surprise to anyone, it just simply drives home the point that your conventional random error estimate is almost always an underestimate. Even in a really well-designed randomized trial where your random error estimates meet most of the assumptions, you're still probably going to have some outcome misclassification that isn't going to be accounted for unless your study is so large that you have no random error in the misclassification mechanism. And the second point, and the last point that I want to raise, is this fourth point about uncertainty in the bias parameters doesn't go away as sample size get large. Well, you could sort of argue that could go away too, because where do I get the information from to parameterize the bias analysis? Well, hopefully I get that from a validation study. If I've done an internal validation study, I measure the sensitivity and specificity in my population, but I measure them with random error. That's the random error that we accounted for when we put distributions around the sensitivity and specificity. But what happens as the sample size of my validation study approaches the size of my study population? Well, two things happen. First of all, I don't really need to do a bias analysis at that point because if I've done a validation study on everyone in my study, I actually know the true value. I wouldn't use the misclassified value. But even if I did, I would be doing it with distributions around the sensitivity and specificity that are so narrow that they would actually approach the expectation and the variability would go away even in that fourth parameter. So even that can approach zero as we have perfect information on the bias parameters, which makes sense because again, if we knew exactly what the bias parameters are, then we would have perfect certainty. We would essentially be doing the correct analysis, in which case we would be perfectly accounting for all of the error. So I'll stop there, but the I think the lesson here is, what is systematic error and what is random error is not always completely obvious, but understanding what they are is really helpful in terms of thinking through what your conventional random error estimates are, and then how we think about accounting for total study error. So I'll stop there, but and I'm happy to take any